Greetings. My name is Mike Levis, and I'm an instructor with the Mount Hood Ski Patrol Avalanche Program. In previous discussions, we have covered weather and snowpack. Today we will cover the last leg of the AVI triangle, terrain. So we have three primary objectives we need to accomplish today. First of all, we need to make sure we can identify basic terrain features that indicate increased avalanche risk. Secondly, we need to identify terrain features that indicate potential avalanche slide paths. And thirdly, we need to be able to recognize terrain traps. This information will all be critical in safe route planning, which we will cover in detail in a later module. When assessing terrain, and in particular when assessing whether there is potential for an avalanche on a particular slope, there are several key questions which we should be asking ourselves. Is the terrain capable of producing an avalanche? If an avalanche occurs, what are the consequences? And what terrain features give us clues to avalanche risk? Let's begin by discussing the factors that will determine if specific terrain is capable of producing an avalanche. The most critical factor is the slope angle or steepness of the terrain. Please note that this is not the average slope angle of a large slope, but local isolated areas of increased slope angle, such as the downhill slope on a snow pillow, where increased shear stresses can result in weak layer failure. Other factors include elevation, slope shape, slope aspect, and surface roughness. We will discuss each of these in detail in the following slides. Let's look at slope more closely at slope angle. Slopes of almost any angle can slide given the correct conditions. However, the most likely angle for avalanche activity is in the range from 35 to 45 degrees. This is significant since these slopes are the ones that are most eagerly sought out by backcountry skiers, equivalent to a black diamond run in a ski resort. For angles significantly higher than 45 degrees, snow will slough off the face of the mountain due to gravity, and there'll be little slab formation. For angles significantly less than 35 degrees, the shear forces on the weak layers are reduced to the point that they will fail only under the most unstable conditions. Note, all of the above is primarily oriented towards slab avalanches. Wet slides or slush avalanches can occur at much lower slope angles, but these tend to be much less dangerous, as we have discussed previously. So the key takeaway here is slope angles in the 35 to 45 degree range are the bullseye for avalanches. Note that another consideration is the position of the skier or snowboarder relative to the high angle slope. Think about, for example, a skier traveling in a flat area below a slope of 40 degrees. It is possible for the skier to cause the collapse of a buried weak layer. The fracture can then propagate uphill to the higher angle slope, causing a slide that then comes down onto the skier. The lesson here is to be aware of all the slopes in the 35 to 45 degree range in the vicinity of your route of travel. And always ask yourself, what are the consequences of an avalanche on any of these slopes? I will also like to emphasize again that the starting point for an avalanche may be very local, isolated high angle point in the 35 to 45 degree range on an otherwise lower angle slope. These local points of high stress can trigger a slide that will bring down the whole slope. Note there's some variation in the slope angle bullseye based on the nature of the snowpack. In the maritime region, such as on Mount Hood, the slope angle bullseye is in the 35 to 45 degree range. The range is slightly lower in the intermountain region and lower still in the continental zone. This is due to the colder temperatures resulting in weaker buried layers in the drier snow conditions. So what actually causes an avalanche in these high angle slopes? The failure starts at the interface between the consolidated layer on the surface and the base layer below. The consolidated layer and the base layer are separated by a weak layer. As the slope angle increases, the shear forces on the weak layer, primarily due to gravity, increase, leading to shear failure. This shear failure is the source of the whomping sound associated with slab avalanches. Note that this shear failure can happen over a whole slope at the same time, as local failures increase stresses on adjacent areas. This shear failure alone is not enough to cause a slide, however. In order for the slab to actually move down the slope, it must be disconnected from the mass of snow on the side of the mountain. There needs to be a tensile failure that creates a fracture that frees the slab to move downhill. The tensile failure often happens at high stress points such as tree wells, buried rock formations, or other features that magnify stresses in the snowpack, leading to fracture. So the shear failures on the buried layer increases stresses on these high stress points, causing tensile failure. If the tensile failure propagates across the slope from one buried rock formation to another, for example, the whole slope is free to slide, resulting in a large slab avalanche. So if the slope angle is so critical, how do we determine where the slope angle is on a particular slope? Well, we could try by eyeballing the slope, but this is notoriously inaccurate. And as we saw on the previous slide, a few degrees can make a big difference. I would recommend the use of an inclinometer in order to get an accurate reading. We will practice all this in our field session, as well as discussing where exactly on the slope to measure slope angle. The message for today is don't guess or eyeball the slope, measure it. So let's look at some of the other terrain parameters that can impact whether a slope would produce a slide. Let's start with elevation. So assuming the same slope angle, what do you think the differences would be between a slope at 10,000 feet versus one at 5,000 feet? Well, at higher elevations, we would expect colder temperatures, so the nature of the snowpack would be different. We would also expect more snow and more wind loading on lee slopes, which would increase loading on any buried layer. At lower elevations, we would expect lower temperatures, possibly more rain events. We would expect a thinner snowpack and a greater stabilizing effect due to trees and other vegetation. So for the same slope angle, we may have conditions at higher elevations that produce avalanches, while lower elevations are quite stable. Another important terrain variable is slope shape or contour. Convexities and concavities in the slope can magnify stresses in the snowpack. Convexity in particular creates local areas of higher slope, increasing tensile forces, and can lead to tensile failure. Convexities are often the starting point for a slide. Concavities tend to be more stable. The compressive force of the uphill snow is supported by the snow below it, resulting in increased stability. Note that this effect is greatest on small slopes. On larger slopes, the effect of the slope angle is far more significant. The orientation or aspect of the slope is another terrain parameter that can affect the likelihood of a slide. There are two main considerations influenced by aspect. The first is the direction of the wind. As we discussed in previous modules, wind can greatly increase loading on the lee side of ridges or knobs. The increased wind loading increases stresses on the snowpack and increases the likelihood of a slide. The sun exposure can impact snowpack stability and hence the likelihood of a slide. Northern or sheltered aspects tend to remain colder and the snowpack will take longer to stabilize. Southern or sun-exposed aspects tend to be warmer and stabilize more quickly. Local terrain features such as ridges, knobs, and notches can magnify the effects of the wind and sun exposure. Surface features such as trees, rocks, and other buried objects provide anchors to the snowpack and increase stability, up until the point that they're completely buried. Once they're buried deeply in the snow, they have little stabilizing effect and may act as stress concentrators, as discussed in the previous slide. Partially buried boulders will create a different temperature profile within the adjacent snowpack, which will influence snowpack metamorphosis. Trees can act as anchors and provide protection, provided they are closely packed. Widely spaced trees offer little protection or stability. The general rule of thumb is that if you can ski through it, then they're too widely spaced and will offer little protection in the event of an avalanche. So when assessing the terrain for potential safe routes to travel, keep these questions in mind. Where are the trees? How dense are they? How big are they? Are boulders on the slope that is near the bullseye of 35 to 45 degrees? Are they exposed to the sun? We'll discuss this in more detail in our discussion on safe travel decision making. One of the key questions we posed at the beginning of the module was, if there is an avalanche, what are the consequences? Practically speaking, we really aren't interested in avalanches where there's no possibility of harm to people or damage to property. However, even minor avalanches can have severe consequences depending on the terrain involved. Let's look at some examples of this. Terrain traps are gullies or other depressions that magnify the effect of the avalanche. Relatively small amounts of snow can pile up, resulting in much deeper burials if a skier is in the gully when an avalanche occurs. Avalanches above a cliff can also pose a severe risk. A small avalanche that would normally not be of significant concern can be fatal to a skier pushed over a cliff by the force of the avalanche. Trees also can be a severe hazard. A skier caught in an avalanche and strained through a cluster of trees can be severely injured by impact trauma. Crevasses are always a hazard on glaciers. They can be particularly dangerous if they're below someone caught in an avalanche, resulting in a very deep, usually fatal burial. One of the best indicators of avalanche risk is a past history of avalanches. It's therefore very important to recognize the signs of past avalanches. On this slide and the next several, we'll identify terrain features that indicate past avalanche activity. In this slide, for example, there are clear avalanche tracks from past activity. Multiple start zones feed into converging tracks devoid of trees. Any attempt to ascend this face should avoid these tracks and start zones. This slide shows several features that are indicative of past avalanche activity. Vegetation patterns offer great clues to past avalanches. Look for areas where trees are missing, broken trees, trees missing branches on the uphill aspect, or younger trees of a different species surrounded by older growth. Other clues to look for are rock debris deposited along and at the bottom of a suspected avalanche track. This slope also has multiple potential start zones feeding a wide track. Can you spot the ski patroller in the trees in this photo? Ski patroller is attempting to traverse this slope in a safe fashion by staying in the trees. This photo clearly shows recent avalanche activity. The crown of the slab avalanche is clearly visible on the right-hand side. So looking at this, what conclusions would you draw about the slope on the left-hand side when you have the clear avalanche signs on the right-hand slope? Similar aspect, similar steepness. What conclusions would you draw on the left-hand slope? This slide shows the leeward ridge side of a ridge. Snow from the ridge falls onto the steep slopes below and can trigger an avalanche. Can you see the tracks in this? There are several of them. The wide one in the center of the photo is the most visible. The tracks in this case are relatively short, but the consequences can be severe if you're caught. We have discussed terrain considerations relative to avalanche risk, and the key questions we must always be asking when traveling in avalanche terrain. Is the terrain capable of producing an avalanche? Slopes greater than 30 degrees should always be suspect. The bullseye where most avalanches occur is for slopes between 35 and 45 degrees. Question number 2. What terrain features are there to indicate avalanche activity? Start zones, avalanche tracks, and vegetation patterns from previous avalanches are all indicators of avalanche risk. Question number 3. What are the consequences if I'm caught in a slide? Many terrain features such as terrain traps and cliffs can greatly magnify the consequences of an avalanche. Be obsessed with consequences. The bottom line is to avoid steep slopes when snow is unstable. Do not enter them or travel below them. So this wraps up our discussion of terrain. We've now covered all the legs of the Abbey Triangle. We will now move on to discuss how to assess snowpack stability and safe travel planning.